to the cloud. So, hello everyone. Welcome to the ITC Colloquium this week. We have a pleasure of welcoming Anna Schauer, who is a Hubble Fellow at UT Austin. Before that, Anna got a bachelor's degree in physics and master's in astrophysics at the Ludwig-Maximilian University in Munich, and at the time she studied mergers, signatures of mergers in elliptical galaxies, and found that you can actually see them in or that the signatures remain in the velocity dispersion of stars. However, when she moved for her PhD to Heidelberg, she also switched the topic and then started simulating physical conditions in the very early universe and like the formation of the very first galaxies. And when she moved as a Hubble Fellow to UT Austin, she kind of continued along this line of research, but really focusing on what these conditions mean and how they affect the formation of the very first stars in the universe. So we'll hear about both her theoretical work and also some very interesting forecasting that I'm super curious to hear about, because who wouldn't want a telescope on the moon? So we should all make a case for that. So with that, please, Anna, take it away.
Thank you so much. It's a pleasure to speak virtually in Boston. Thanks a lot for having me. So as Anna said, I will talk today about the formation regions of the first stars. And for that, I would like to start with giving this time evolution of the universe overview. So we have the Big Bang on the left, and we have our present day universe on the right. And after the cosmic microwave background emerged, everything was more or less dark and not ionized in the universe. And it was really the first stars that formed roughly between redshift 30 and 10 that started to light up this universe. When we now look for observational tracers, we can probe some very early galaxies with our current instruments. The record holder galaxy is at the moment at redshift 11, and the record holder supermassive black hole is at redshift 7. And we hope to push this a little bit further out to redshift 14, 15 with James Webb. But those galaxies that will be observed will be biased towards the very massive end. So in order to really understand how those individual star formation regions, how those very first galaxies, those so-called mini-halos work, rely on numerical simulations or semi-analytic models. And this is what I study most of my time. So I have this nice set of cosmological simulations. You can see here a density slice through my entire simulation box. It's 1 co-moving megaparsec cubed in size. And the nice thing about those simulations is twofold. One is that we have primordial chemistry included. So I will talk about it in a second, but it's important to treat the formation of molecular hydrogen correctly when you talk about the early universe, because it's your main coolant at high redshifts. And the other nice thing is that we have a high resolution, and we have this high resolution uniformly throughout our whole simulation box. So we don't only zoom into a few objects, but we can treat all those tiny galaxies that are forming with the same high resolution. And our resolution is roughly 100 solar masses in dark matter and 20 solar masses in gas. And because we don't form stars directly in the simulations and don't have any supernova explosion, metal enrichment, we can't run those simulations for very long, and we stop our simulations at a redshift of 14 or 14 and a half in some cases. So the redshift range we cover is from 200 down to 14, 15. So as I said, those very first galaxies, those so-called mini-halos, form massively in the simulation. And I'm zooming in here into one of those regions, and you can see that those form at the intersection of those filaments that we start to see. And let's talk a little bit more about this. So the physical properties of those mini halos, you can see here a small density slice of a small region of my simulation. We have a very filamentary structure. The gas is mostly following the dark matter. It sits in those filaments. And of course, our stars form out of the most dense gas that's in the center, so that's indicated by the dark green here in this plot. And the mass of those extended objects, of those mini halos, is in the mass range of a few 10 to the 5 to 10 to the 7 solar masses. When we look at the temperature of exactly the same part of the simulation, you can see that the temperature is relatively low in those low density regions, just because the universe expanded and we have adiabatic cooling, so to say. And then whenever we have a high density region, we have shock heating. So the shocks heat up the gas to temperatures of yeah, it depends on the mass of the object, but a few 1,000 to 10,000 Kelvin. However, at the very centers where the gas is very dense, we can do the comparison. So here you have like a little bit of a lower temperature region. Here you have a bit of a lower temperature region, and here that is at the same position as our high density gas. And if you look at another property, the molecular hydrogen, this is exactly where we find our molecular hydrogen. So this is just a conceptual view that shows that molecular hydrogen really drives the cooling in those high density regions. Because we don't have any metals, atomic hydrogen can only get you to 8,000 Kelvin. So with molecular hydrogen, you can cool to those lower temperatures, therefore drive the Jeans mass down, and therefore you can start to form stars. However, the formation is not just hydrogen and hydrogen, it needs to go via a formation channel, either of H- or H+. So this is why it's important to include a full network of primordial chemistry in those simulations, and luckily we can do that. So now let's make the picture a little bit more complicated, apart from just hydrogen and molecular hydrogen. When we look at the very early universe, there's one effect that really matters, and that's the so-called streaming velocities. So again, here I have my time evolution slide, and then going to before recombination, we had this tight coupling of gas with photons. And this is what the streaming velocities ultimately origin from. So on the right, I have a very conceptual view only of the gas and dark matter structure. So we see that we have a little bit of an overdensity in the dark matter in the center of my conceptual view. Dark matter is indicated by those dark big blobs here. And then what happens is that the dark matter fluctuations can increase. So the dark matter is falling towards its gravitational center. However, because of this tight coupling, the gas can be pushed outwards in some regions of the universe. So when we look at this, we have here an over density. The gas is coupled to the photons. We have too much pressure. So actually what happens is that the gas is pushed outwards from this overdensity. And then when we look at this in some regions of the universe, we then have exactly the opposite velocity of the gas and the dark matter. Whereas in other regions of the universe, we are moving with a similar velocity. So this is basically baryonic acoustic oscillations. And when we now look at this, this is an effect that happens on very, very large scales of the universe. So here I show you a conceptual plot with a side length of 400 co-moving megaparsec. We have this velocity difference imprinted in the universe, and it's a very large scale effect. This means that we have single boxes that have roughly the same offset velocity, and we can run simulations of roughly the same offset velocity just by taking small boxes and just simulating one region of the universe that has no relative velocity between gas and dark matter, and we can run another simulation that is a fraction of the universe that has a high offset velocity. Those velocities are distributed like a multivariate Gaussian. And another important thing is how big are those? So the root mean square velocity of that is 30 kilometers per second at recombination. And as the universe expands, this velocity decays. So this is also saying why it is important at high redshift, because those velocities are larger, and also because our galaxies that are forming, they are smaller. So relatively speaking, the velocity offset between the gas and dark matter in some regions of the universe is quite significant compared to, for example, the escape velocity of the galaxies that are forming. So I run those different simulations. I don't only have the simulation with no streaming velocity. I really pick out 4 different regions of the universe with different streaming velocities. And I run those 4 different simulations. They also have the same properties. So it's 1 co-moving megaparsec is the side length. And I've shown you this picture before. This is the density slide of my whole simulation box at redshift 15. And this is the simulation with no streaming velocity. And now I'm going to show you the simulations that do have a non-zero streaming velocity. So this is no streaming velocity. This is a slight streaming velocity. It increases. And this is the largest one I simulate. So what you can see here immediately is that we kind of have a structure washing out. So we can really see already on this large scale that streaming velocities have an important effect on those high redshift times for the density distribution, and because in high density gas regions, you form stars also for the star formation. So I have the same plots again here in the top row. So the top row was the last 4 slides. And then when you zoom into one region, I show you again the density slice here, now just with a slightly different color scale. And you can see here again that this structure is washed out because we have this large scale offset velocity. I choose it to be in X direction. That's completely arbitrary, but you can see that it's washed out in X direction. And what you can also see is that the high density region decreases. So we have the gas in the highest density region in the high streaming velocity case is much lower than in the no streaming velocity case. And if we zoom in even more into my simulation, then we can see that even more clearly. So the conclusion of that is that those streaming velocities wash out those structures, and then the density decreases when you go to higher streaming velocity regions. And then you can see that this halo, if you can call it a halo, not just a filament, doesn't have high density gas anymore. So of course it can't form a star in there. So we move to different, or just a couple of halos can still form stars in those streaming velocity regions. Stepping back from that, I would like to consider the second important effect that prevents star formation at very high redshifts, and that comes from the first stars themselves. So as the first stars start to emit light, they start to emit also light in the so-called Lyman-Werner bands, and those provide negative feedback as well. So quickly talking through it, Lyman-Werner radiation is UV radiation between 11.2 and 13.6 eV roughly. It's in discrete energies, and this UV radiation can destroy molecular hydrogen. It can destroy it by a 2-step process. It's a molecule. You can enhance the rotational energy, then it starts to vibrate, and then it can eventually break up and fall down to a state where it is broken apart. This so-called Lyman-Werner radiation, we cut it off at the ionizing limit, and therefore we are in our universe that is neutral, and this Lyman-Werner radiation can mostly freely travel through the universe. Unless you have a lot of molecular hydrogen, then you start to have a self-shielding process. So molecular hydrogen is emitted by the first, Lyman-Werner radiation is emitted by the first stars and can destroy molecular hydrogen, but molecular hydrogen is critical for forming those first stars, and therefore it makes it harder to form fast stars as soon as you have Lyman-Werner radiation. Looking at the same similar set of simulations. I have the same simulations, and now I turn on progressively higher Lyman-Werner backgrounds. So here you can see again a full slice of my simulations at redshift 15. This time I show you the molecular hydrogen abundance, and in the case where I don't have a Lyman-Werner background, you can see that the just average value in the universe is much higher than when I have even a small Lyman-Werner background. And then I'm zooming into the same halos again. And when I zoom into the same halo, you can see that also the molecular hydrogen fraction in those halos, in the case of no Lyman-Werner background, is higher than when you have a Lyman-Werner background. However, zooming in even more, you can see it even better. You're even able to retain some of the molecular hydrogen, even if you have a strong Lyman-Werner background, because of this self-shielding effect from the molecular hydrogen. And then what I really do with all those data, so I have a set of total 12 simulations where I turn on different streaming velocity values, different Lyman-Werner backgrounds, and I run all those combinations of them. And this is those are two of my main result plots. I then search for how massive are the galaxies that are able to have high density gas, and therefore what mass do the galaxies and mini-halos have in order to form stars. And I show you here the least massive galaxy as a function of redshift for all those combination of Lyman-Werner backgrounds and streaming velocity values. When I don't have an effect, my minimum halo mass, so the least massive halo that passes a certain density criterion that I say is enough to form stars, is rather constant, and it's at a few times 10 to the 5 solar masses. Then when I include a Lyman-Werner background but no streaming velocity, it goes up to this dark gray line, so increases just a little bit, including a stronger Lyman-Werner background, increases it quite a bit. And then I move to this whole set of new color here in my plot as soon as I include streaming velocities. So if I don't have a streaming velocity, I do find those halos with a few times 10 to the 5 solar masses that can form stars. As soon as I'm in the regime where I have streaming velocities, this star formation mass threshold moves to 10 to the 6 solar masses and higher. And then the Lyman-Werner background in addition increases this mass, because then the galaxies don't only form later, but they also have to have a higher mass, so they have more gas that can self-shield them against the Lyman-Werner background. And when I move to my outlier region, where I have a really high streaming velocity of 3 sigma and a Lyman-Werner background, I reach the atomic cooling regime, so a really high mass threshold for star formation to take place. And on the bottom panel, it's a very similar picture, but here I search for the average halo mass of all my star forming objects at that redshift. So the top panel shows the minimum halo mass, and the bottom panel shows the average halo mass, because when we want to transform those results into semi-analytic models that are maybe important for 21 centimeter radiation and things similar like that. We're not only interested in the outlier object, but we're interested what the average mini halo in the universe does. And of course, when you move away from the least massive object to just like the average object, your masses generally increase. But the overall picture is that both effects, Lyman-Werner radiation and streaming velocity, increase the mass threshold for star formation. We don't see direct redshift dependence. It's all very stochastic, and due to the relatively low numbers of mini halos that we have, even though we have quite a few, So we can't see a clear redshift dependence. And then when you compare the two effects, which one is stronger, you see that streaming velocities have the stronger effect, but those two effects ultimately add up. So now I'd like to go back to my first slide and talk about the observational prospect. So we talked about that we need mostly numerical simulations and semi-analytic models to probe the formation of the first stars at those early redshifts. You can actually reach some of those first star formation regions with a 21 centimeter radiation, but for that you probe a global signal. So if you want to really observe or get information about a single object, 21 centimeter radiation can't do that, or can't do that yet. But now for like those last few minutes of my talk, I wanted to turn the question around and ask what kind of telescope would you actually need in order to observe those first mini-halos, those first star formation regions. And for that, we played a quite simple game. So what kind of telescope do you need? And we defined 3 criteria that such a telescope needs to fulfill. One is it needs to observe enough sources in the sky. We don't want to just point a very expensive telescope somewhere and not pick up any sources. So the number density of sources in the sky needs to be sufficiently high. Of course, we need to be able to see those first objects. So we need to design the telescope that we can pick up those very dim galaxies that are not filled with a lot of stars. So the brightness of those population 3 star clusters is important. And then if we see one, we want to be sure that we see one and we don't accidentally see a brown dwarf. So just walking quickly through it, we took different models for the brightness of the population 3 star clusters. We took 3 different models. There are many more, but we kind of wanted to span a model range. And here I show you, we have single population 3 stars without nebular emission, and then we have here a time evolving population 3 SED that considers nebular emission, and both of those are taken from the literature. We choose the Yggdrasil model from Zachrison 2011, and also my postdoc advisor's model for a single massive population 3 stars here. And when you now put the light of a typical population 3 clusters, which we take to be 1,000 solar masses as the fiducial mass, through your James Webb filters. We choose the James Webb filters because they probe nice wavelength ranges. You can see here the flux on the sky, also translated into the RB magnitude. And if you want to observe those first star clusters, what you can see is that you need to roughly probe a 39th AB magnitude. So if you establish that limit, what this leads us that we need is that we need roughly a 100-meter mirror. And because we need to probe the wavelength regime that is not observable from Earth, we need to go into space. This can either be done in space directly, or another possibility is on the moon. And for that, we're very happy that there is a project proposed more than a decade ago by Roger Angel and his collaborators to put a liquid mirror telescope on the moon. And if we compare what we need from our paper to what this telescope has, it would be a very good telescope to do this with. And the choice for a liquid mirror is because you would need to transport less material into space, and therefore, even though building a 100-meter telescope on the moon can of course never be cheap, but it would hopefully reduce the cost to have a rotating mirror that can then be coated and moving it to the moon would be cheaper than having it directly in space. So this is why we say that telescope proposed by Roger Angel would probably fulfill those 3 criteria and be a good way to observe the first stars directly. So I leave you with my conclusions. I study minihalos that have those masses of a few times 10 to the 5 to 10 to the 7 solar masses in my numerical simulations. It's important to include the effects at high redshift, streaming velocities, and Lyman-Werner radiation if you want to study atypical star formation regions at those early redshifts. It's currently out of observational reach, but we could observe those with a, for example, 100-meter telescope on the moon. So I look forward to the extended discussion round. Thanks a lot for your attention.
Thank you, Anna. Very thought-provoking. As a general reminder, if you have a question, just send me a direct message chat so that I can kind of guide or group questions on the same topic this way. And we have a first question from Avi. So Avi, please go ahead.
Yeah, very excellent talk, Anna.
Thank you.
Question, at what flux limit do we expect sources to cover the entire sky? So overcrowding will be an issue. Of course, if you know the redshifts, you can separate them in the 3rd dimension, but just in 2 dimensions, at what flux limit do you know we get overcrowding?
I don't think that overcrowding will be a big problem. Like at some redshifts, the population 3 star formation density dives down again. I don't think that we nowadays have still those very tiny galaxies forming. So you basically then lose the many galaxies that many small mass galaxies. Like after some time, everything has either already formed stars or will never form stars, I guess.
Right, but which fraction of the sky is covered, do you know, by galaxies? Out to redshift 20, 30?
So if you look at the cumulative number,
not just the fraction, each galaxy has a size, right? So which fraction of the sky is covered?
I would say it's a small fraction. At the moment, we have the telescope designed in a way that those first galaxies would be point sources.
Okay.
And if you look at the cumulative number of those galaxies between just redshift 10, which is the lowest we go down to like the highest redshift that we expect first stars, we expect, like even with our most optimistic model, we expect like 1,000 per square arc minute. And I'm pretty sure that you will always, like any detector will have many, many more pixels than that. Mm-hmm. So I don't expect that we will just like have a bright like image, and therefore we can probably pick out those sources.
Thank you.
Just as a follow-up, so are you mentioned that with your in the simulations looking at the star clusters of population 3 stars, and is this one cluster per mini halo or?
Yeah. Okay. Yeah. So we assume that we have one star cluster forming. Like the POP3 IMF is not yet known. It's not yet known if it's one star or if it's a couple of stars, but slowly the literature moves towards it's probably one cluster of stars. So we assume in our model that we only have one, because those stars also don't live very long, and as soon as they explode, we have metal enrichment, and then we have population 2 stars instead.
Thanks. And Julian Munoz, I think, had a question along similar lines, so please go ahead.
Yeah, so thanks for the talk, by the way. That was really great. This is a topic that is close and dear to my heart. So So yeah, I had a couple of questions about this. The first is kind of similar. Like, do you have enough statistics to figure out some like stellar formation efficiency for the mini halos, or are they just bursty? They form once and they stop. Can we figure this out?
So for my simulations, because I want to resolve the mini halos, I don't do this very high. I don't do the highest resolution point at the center of the mini halos. So I actually don't form stars directly in my simulation. So I don't have statistics about the stars because the stars don't really form in my simulations. Is this your question?
Well, I guess my question is like once you form the stars and they start emitting Lyman-Werner photons, you only get one burst of pop-3 stars, or are there more than one burst by the same halo?
As soon as I have a second burst in the halo, it wouldn't be population 3 stars anymore, because they are massive, they are short-lived, just a few mega years. Yeah, but I don't form stars directly in my simulation. I just check for density criterion, and then I say, this is enough. If you had this whole star formation prescription, that you would form stars.
Okay, cool. And the other question related to this, and I have more, but I'll let other people ask. But the second related question is, what you showed at this density smooth plot, when you have larger velocity, you smooth, like this, the Hirata and the Chris Hirata and Sedljakovic effect.
Yes, yes.
Do you also see a decrease in the number of halos? Is this like this is kind of like orthogonal to the question you're answering, right?
Yeah. So there are, what happens is that because the gas has a harder time to settle in the dark matter halos, then one thing that happens immediately is the gas fraction in the dark matter halos decreases. This then means that those halos are a little bit less massive. So we all know that dark matter, there's much more dark matter than gas, so the gas doesn't play a major role. But if you have a little bit less gas in those halos, your mass is a little bit less, and therefore your halo mass function shifts just a tiny bit, but that's not a big effect.
Okay, cool.
Yeah.
So you do find that, you agree with those results as well. Okay, yeah. Thanks.
So we have some questions about kind of observational signatures like at low redshifts, but let's just stick a little bit about the condition of the high universe and exhaust those questions first. So Morgan, please go ahead.
Sure. Yeah. Thank you so much. So I was wondering, you were talking about, whether these clouds fragment and form a cluster versus form a single star. And can you talk a little bit more about that in the context of your simulations with varying levels of sort of ionization in the background? Like, does the cumulative effect of a cluster with the same mass produce, like, where does that fall on that sequence? So can I understand that series in the context of that question, or are those really separate?
So you mean, I'm not sure if I understood.
Okay, let me try again. Sorry. So you were showing us a really beautiful sequence with different amounts of
Lyman-Werner background.
Lyman-Werner background, and then different amounts of H2 as a result. So I was wondering, does when some pop3 stars form, do they contribute to that, or is that really negligible?
So in my simulations, because I don't form the stars directly, I treat the Lyman-Werner background as an external background.
Right.
Of course, the Lyman-Werner background is built out of the radiation that is coming from those first stars.
Yes.
So yes, it's so to say a circle. If you consider those large scales, then you prevent some stars from forming. Therefore, also your Lyman-Werner background doesn't grow that much because those stars don't emit the Lyman-Werner radiation. Yeah.
So then what I was wondering is, you were talking a little bit about whether clouds fragment and form a cluster versus a single large star. How does that affect, like, for a given amount of star formation, what the Lyman-Werner background would be? Like, can we understand those two as linked? And and think about, your sort of, I understand that there are simplifications in that sequence of simulations, but can we understand those as sort of along some continuum?
So if you have a very different IMF, the amount of Lyman-Werner photons emitted per solar mass formed into stars changes. If you want to simulate this very self-consistently, you need to then also do a model of population 3 stars and consider their IMF. However, those simulations I don't think will be like very feasible if you have both the background produced by your stars and the, so to say, vicinity regions where the Lyman-Werner background is, or the Lyman-Werner radiation from the neighboring halo is of course stronger because of the really, really large regions of the universe we're talking about. So this Lyman-Werner radiation can travel roughly 80 megaparsec before it is moved towards other bands. Yeah.
Okay.
But yeah, if you want
Very
to consider like the neighboring halos and take into account that if you're sitting close to a halo that formed a lot of stars, this Lyman-Werner radiation then will inhibit star formation in the neighboring halo, and then it depends on what the spectrum from the population 3 star in this first halo that forms stars look like.
Interesting. Thanks so much.
Yeah, of course.
Okay, so I think now is a good time to sort of move on. What can we learn at lower redshifts about these processes? So Rohan, please go ahead.
I mean, to be clear, the lower redshift I'm asking about is redshift of 15-ish, right? So like, yeah, so I was curious, like, is there like any hope whatsoever with like these redshift 10 to 15-ish, maybe L-star galaxies of placing constraints on your models? Like, do the models like diverge in any observable way? And in a similar context, I was curious what you made of like, helium-2. Like there's a lot of people like applying for gobs and gobs of JWST time to measure helium-2 to constrain like POP3 populations at these redshifts. So like, I surmise you're not very optimistic about helium-2 either then.
So it's helium-2 because the stars are massive, right? So they produce a lot of helium-2. And I think you're talking about CR7 and what follows from that.
I mean, not just CR7, but like, like at high redshifts now, people want to like, spend whatever 100 hours with NIRSpec to like measure helium-2 at like, redshift 10 or whatever.
Yeah, I'm sure there are the more massive outlier galaxies, and those might still have like a surviving population 3 star. We see that star formation shifts on average to lower redshifts if you're in those streaming velocity regions. So you could very well have like a galaxy, a mini halo, an atomic Cooley halo that formed a population 3 star that then still lives and has merged within a larger object and then is still emitting some of the helium-2. But if you look at how much flux is produced by just a small region, a small number of population 3 stars, this flux criterion cannot be met because you only have like mini halos are small and therefore you don't have many stars. Even if you move to a star formation efficiency of 1% of the gas, it's hard to observe that. Just because like we say with James Webb, you can't observe those population 3 stars, those mini halos, because the amount of mass in stars in such a typical mini halo, atomic cooling halo is small. That's the biggest hindering to observe those mini halos directly. you can very well have an exceptional object, but that's very rare, and we won't be able to probe the typical mini halo.
Does this answer your question, Herman?
Yeah, thanks.
Okay, I think Julian had a comment related to this, so let's go with that first.
Like, I think if you go to Redshift 15, I think there's hope to detect these things indirectly, and I don't know if that would be like good enough for most people. But like these things definitely do matter. Like in terms of observables, as Rohan was saying, that like disagree or like diverge with different prescriptions, the 21 centimeter line will diverge a lot. Like if you go early enough where these things are the main halos forming, then it does matter a lot. But then again, that is indirect. You're not seeing these objects, you know, one at a time. But I think there's some hope there.
Yeah, if you, for example, look at the 21 centimeter signal, it's already now important for the global signal to include streaming velocities. Otherwise, your properties just change. Yeah, I don't know if it's the Wiesbaum paper from 2012 or the Fialkov paper from 2014 who had the differences for the 21 centimeter global signal included, if you have streaming velocities included in your prescription or not. And you see that the global signal has a different profile as a function of redshift.
Right, so not only can we detect the POP3 stars, we can actually tell the effect of velocities of the effect of Lyman-Werner feedback on these stars. So again, indirectly, but I think there's a lot of a distinguishing power.
Yeah, and I think for really nice 20 centimeter signal measurements, it would also be good to move to the moon. So we should, yeah, it would be amazing if that happened.
But speaking of sort of maybe in the less direct probes, I think Josh had another question. Mm-hmm. So Josh, please go ahead.
It's the old question that many, including Avi and Fokker and others, have thought about, namely GRBs at high redshift, which almost certainly, of course, nobody's proven this, are going to result from POP3 stars, which are massive. And so this is something that would tell us, you know, something about the epoch of first POP3 star formation, you know, because that's something that future facilities that are being proposed now, in fact, have been proposed in the current decadal survey, could really do. And it would not be really as expensive as a 100-meter telescope on the moon, much as that might be interesting. So I just wanted to point that out, which it will not, you know, it will only tell us about the redshift dependence. It won't tell us anything about structure of mini halos, presumably, but neither would the 100-meter telescope on the moon, right? You're not going to resolve anything.
Yeah, it wouldn't resolve those mini halos, but alone from the colors, you could infer some properties.
Yeah.
Yeah. How frequent are those GRBs?
Well, they could be very frequent. We have very incomplete knowledge, not because of the GRB detection problem, although that can be greatly improved, and that's also being proposed, but the lack of prompt follow-up infrared imaging and spectroscopy. As I've pointed out to, you know, others here before, there's a very large fraction, I mean, it's not a negligible fraction of GRBs that are optically dark, and that, you know, is not then followed up in any systematic way with prompt JHK imaging and then spectroscopy, which is, of course, the only way to resolve whether these things are high redshift and therefore optically dark. So that's the biggest challenge. But there's a very easy quote unquote solution for that. A 1.5 meter or even 1.3 meter telescope at L2 that can rapidly slew, which we've proposed to the decadal survey, something we call the Time Domain Spectroscopic Observatory, TSO. That would do it with existing swift bursts But if you can go fainter than Swift, and if you can cover more of the sky, like all the sky, then you have the ultimate package. And you could really trace POP3 formation back to the very beginning. So I hope this happens.
Yep.
But very nice talk. Thank you.
Thanks.
So can I just follow up on this? What do you think Anna would take from the more simulation perspective to produce like realistic forecasts of how many GRBs you would expect in from these POP3 stars? And like, do you see like this theoretically happening in the next, say, 5 years?
Yeah, I'm really not an expert on GRBs. I don't think I can really comment on that, unfortunately.
Oh, Avi, go ahead.
Yeah, there was a recent flash that was argued to exist at redshift 11, and that is still being debated. And there were a couple of papers on the archive, one of which claiming that it's actually just a satellite flash, terrestrial foreground. But one could potentially, with sensitive enough instruments, as Josh was talking about, detect not only GRBs, but also supernovae, because massives, if indeed the mass function is tilted towards massive stars, the supernova rate is quite substantial given the star formation rate at those redshifts. So we could potentially see pair instability supernovae with sensitive enough telescopes, and they will overwhelm the luminosity of the galaxy in which they are embedded. So that would be a very nice way of probing those galaxies, because you would see the supernova and then you will know that there is a galaxy behind it. It will be sort of a flag.
Yeah, I'm a bit skeptical about the pair instability supernova detections because they only live for such a short amount of time.
Right. So you need a transient survey rather than one snapshot. You need multiple snapshots to see the time dependence. Yes.
Yeah.
And you need it covering a very large fraction of the sky, which is never going to happen with JWST or anything else. So that's the advantage of GRBs. You get a trigger, and then you put a big telescope on it. So it's a very direct way to go about this.
Yeah. So what would be needed is pretty much the opposite of what we propose here, which is this telescope that just looks stationary in one direction to get as much light over as long as a time frame as possible. But with a pair instability supernova, I think it's hard because they exist for only a very short amount of time. And
yeah, times 1 plus z, right? So we gain a factor of 10.
Yeah.
These supernovae can last for up to a year, and 10 years is a long time.
Yeah. 10 years, like for our models, we assume like stellar lifetime of a few million years. Right. So it's still a factor of 10 to the 5 off, and then
yeah, compared to the stars, but then it shines much more brightly. So and if you have a big enough field of view, you should be able to pick those up. I mean, it's an interesting question to check.
Yeah, for sure. Yeah.
Yeah, it's very messy. Yeah, there's like something intermediate, like between like, that is, say, doable with JWST if there is kind of a region of parameter space that can do that. Okay, so to kind of bring it back maybe to the physical aspect of things, Eric Kita had a question. So Eric, please go ahead.
Yeah, I was wondering if you've looked at what the spectrum of the turbulence is with respect to the size scale of the stars, clouds that form the stars, or the minihalos. And the background for the question is that, say, for example, in our galaxy, the thermal energy generally isn't dominant in molecular clouds, because once you manage to cool the cloud down to below the energy density of the turbulence, then the turbulence really controls the fragmentation. And so a few kilometers per second is kind of equivalent to a few thousand Kelvin. So what does your simulation say about that with respect to the mini halos, which you have in the simulation, or the POP3 stars, which you're kind of almost to that resolution?
So you're saying if turbulence plays a role in the centers of the mini halos.
Right. So there, I know your colleagues at Heidelberg have some questions about whether turbulence can support a cloud against gravitational collapse and so on. But nonetheless, the energy density of the turbulence is generally higher than the thermal energy density, as long as you manage to cool it down to, say, 1,000 Kelvin or something like that.
Mm-hmm. We have not checked in detail like this that type of energy. I can like report what I observe in my mini halos at the centers, and what I see there is that I quite often form a disk-like structure. It's not like a perfect disk, but it's sometimes like looks like a fish or something like that. That is rotating. So at some point, like I'm not dominated by the turbulence, but the central core is more like a semi-stable, slowly rotating high-density structure.
The angular momentum then is supporting the mini halos?
Yes, like this inner structure has some angular momentum, and this angular momentum of this inner structure is not correlated whatsoever with the angular momentum of the mini halo scale. That is something my student checked.
Okay, well, that's fine. It's just curious.
Okay, as we are getting close to the end of our allotted time slot, we can go back and sort of look into the more computational aspects. And I think Julian had another question about the simulation aspect.
I do. Yeah, I'm very interested in the simulation. So like I've read your paper, and there was a paper by Eli Bisba, who you also mentioned. And I think Colloquium was the first author.
Yeah.
And so both of your Lyman-Werner feedbacks are much, much lower than the old results because of self-shielding, right?
Yes, yeah.
But their
as compared to the 2001, 2003 papers.
Right.
Yeah.
But their results seem to have a larger Lyman-Werner flux, but lower feedback overall. Like, have you compared against them and see if there's any difference?
We're working on that. One thing that differs significantly is that we choose a different halo definition. So while I take, in terms of code, with like the Friends of Friends halo mass, they take the M200, and that's usually a little bit smaller. So, and then we have another major difference, but that's, so to say, would make the discrepancy even bigger, is that I employ a merger tree, that I only count my halos once they are star forming, and they don't. So therefore, like, unfortunately, this would make our discrepancy even bigger. So yeah, but we're talking and we're trying to figure this out, because I think we want to have a consistent picture. But my guess is it will be largely due to the different definition of the halo masses.
Right, I see. Okay, that's very interesting. Thank you.
Okay, and so just to follow up on this a little bit, it seems like at least at lower redshifts, the different cosmological simulations tend to at least agree on the kind of general picture, because they have they can be tied at the observables in the local universe. And so I wanted to kind of pose this maybe a forward-looking question of, what do you think would take to run your simulations beyond redshift of 14 to where hopefully we will have a lot of observables with the upcoming JWST observations?
I think one thing that would be important would be to couple primordial chemistry to population 2 chemistry. So currently, I'm not aware of any code that both treats molecular hydrogen formation through those H- S+ channels and also treats then metal-enriched universe chemistry. So I think this is the computational step that needs to be overcome to do that.
Can you give us an illustration of sort of how challenging it is? Is it just like that the networks are much wider, or?
You need to trace different elements, and you then need to switch from tracing like H-, for example, to tracing carbon in your simulation. I don't think it's out of the question that this can be done. Like, I think this can follow fairly quickly.
Okay, and the kind of hardware advances, like does it help, or like the GPU architectures or something with on the, I guess, software side with machine learning? Do you think is there kind of some effective ways that those two can be merged, or?
So I'm not sure if machine learning can do much. Maybe if it's studied a comparison between a simulation that doesn't include the primordial chemistry, then with a simulation that does study the primordial chemistry and finds a prescription in the non-primordial chemistry, just adiabatic simulation, that it can then translate to a pseudo-chemical network in the POP2 chemistry or metal-enriched chemistry. I think that might work. Yeah.
Okay. Well, thank you so much for this talk. And
thank you so much for having me.
It was a pleasure. And we had many interesting ideas that kind of came up or were reinforced with this interaction. So thank you everyone for joining, and we'll see you next week again, same time, same place.
Thank you.
Thank you. Bye.
Thank you, Anna.